Alright, time for another draftphysics.com, debatephysics.com, also video presentation. So there's a new person, another teacher, okay, it's called Debbink, something like that, physics, and yeah, I guess it's his last name. Anyway, so it's the same routine in terms of there's lots of little clips of experiments. I guess I would sort of argue not done as well as they need to be. And so this spar used clips from this guy's videos on angular rotational inertia is what he's calling it. So they're claiming there's some concept besides just momentum. All right, and so somehow you can, if you can calculate something spinning. All right, either way, horizontally or vertically. And the idea is you could understand that if I put something and made it spin and then it released it, it would leave it a velocity, like the moon's orbit or something. And the fact is that its rotational momentum is the same as that linear momentum it would leave with. It's the same exact energy. And so what they do is, I just used the word energy. You can't use the word energy without implying kinetic energy. So what they're basically doing, instead of calculating momentum, they're calculating the kinetic energy. Now, obviously, to calculate the kinetic energy, you have to use the momentum. The mv is in there. But it does make a mess out of getting some sort of coherent understanding. And I guess I would argue that the law of the lever, and the fact is that if you take a lever and you move the distances, it's the same thing as rotating something, is just up and downing something. Doesn't make any difference. It's the same velocity. Distance in time is velocity, and that's it. So it's, and they're just squaring it beforehand. Okay, so you could just argue, instead of just giving you the momentum, they're giving you the calculated kinetic energy after one halving and squaring. And for angular rotation, they don't bother with the 1/2, which just makes it even more complicated. So anyway, they have this thing called torque. Torque is just force. As Newton said, twice the force, twice the velocity, 3 times the force, 3 times the velocity. So it's much simpler than they're making it, and then they're making this implication that somehow a light thing going twice as fast, a half mass going twice the speed, is somehow got more inertia. Somehow it's got more resistance to motion, and it only has more resistance to motion if you're calculating based on kinetic energy, because obviously the increase in velocity is a squared function. So you can increase masses all you want and you'll get nice proportional differences, but if you increase velocities, you create all kinds of momentum, and kinetic energy start diverging rather substantially. Anyway, so the video, so anyway, he has this newest video on, and he has some older ones on calculating the rotational inertia, and he's using these different experiments as examples, and the data on its face to me is just wrong. So you're stuck with having to argue the experiment. So I went to the trouble to download 2 of the videos, and so we'll play that, and it sort of makes my point. Okay, it has an obvious error in it, and it can be used by people with, like I said, the spar types who wish to prove something that's not true, and so they can use these broken experiments to do that. All right, so let's go to the beginning and play that. All right, so it's just a rod. It's got a really bad, I would argue, fulcrum or pivot or bearing, because you can see in this first example how it completely fails. The experiment just completely fails to work appropriately, and the only thing you could blame is friction. It should be playing, hopefully. There's no audio with the videos, so you're not missing anything. So in this first test, he has a small weight, and you can't really see everything, but you don't really need to see everything. So it's just a string wrapped around the pole, goes over a pulley with a little weight on it. In this case, there's a 250-gram weight, and the experiment basically completely fails because you'll see what happens. So it's barely rotating, and then it just grinds to a halt right there. So it just stops. Now he says not enough torque. So it wasn't the torque that failed, it was the friction that failed. So obviously the only thing that could have stopped it from continuing to move is somehow the friction increased. So obviously whatever the bearing material is, it's not even, not fair, not something, and that's the only way you could stop it moving. So once it's moving, you not only have to not give it energy, you have to take away the momentum it already has. So it had to be enough friction to not only no longer be able to give it any more motion, it had to take away the motion it had. So it has to be a lot of friction. Just pointing it out. All right, so this is where you're comparing the two circumstances. So you have the two mass in close and the one mass twice the distance out, which exactly by the law of the lever, we're just basically saying this is one velocity, this is two velocity. So that's the only difference between the two, is the velocity. All right, so a half mass going twice the speed, I'm arguing, is exactly the same as the full mass going twice the half mass speed, the half speed. So two mass going one velocity, same thing when they're in close as the one mass going two velocity. Same exact momentum, same work required to move those two things. And obviously the lever itself, the whatever this is, the rotating arm, has a mass and all that stuff, but the only thing you're testing is the change you've made, and the change you made is just either the 4 pounds in close or the 2 pounds out far. And that creates a little bit of extra weight, right? The 4-pound experiment is going to weigh a little more, so it's going to have a little bit more friction. But anyway, so continuing, so just watch the timer on the left, because it does something really dumb really fast. Up there, it did it right away. So it popped an extra 10 seconds on. So, and it's actually 10 seconds. It's not like something happened and anything like that. It's just 10 extra seconds. All right. So they're basically, it's now both started at just about the same time. I'm a little bit off, but it's only, a percentage of a second. And now they're going to rotate, and you can see the same mass is pulling them. So it's 350 grams now. That's that much force in gravity. So they're both being pulled by the same force. All right. And as indicated, they do exactly as I would predict, and momentum predicts it's going to go the same speed, and it does. So there's a half rotation, and that's the full rotation. So you can see the obvious one, the one with the masses further out, is a little bit faster. So it's really 12 seconds to 11.9 seconds, right? Because the 10 is fake. There's 10 seconds extra on that one clock, quite obviously. And this one's a little ahead. So the lighter mass, you can see, is going a little bit faster. And that's because the heavier mass is actually heavier. I mean, it's, it's the same. The momentum isn't going to be changed turning, but the weight on the bearing is twice the weight. So obviously you would indicate that this one should be a little tiny bit slower because it's going to have more friction on the bearing. So I slowed it down, you can just see. So they're basically exactly the same rotational speed, and for whatever reason he has those really messed up numbers there. So we'll just play it again just so you get the point. Driven home, whatever the right terminology would be. So this is the first with the 250 grams, and it completely fails. So again, the failure shouldn't be some blanket statement like, oh well, it's just not enough not enough energy to move it. It obviously was enough energy. It was enough energy to break the static friction, to cause it to start moving, and the only thing that could be accounted for why it stopped is it had to encounter some extra, some harder friction. So there's something about the bearing that was uneven, and now all of a sudden it's plowing into more friction. And that's the only thing that could have stopped it. Alright, and here's the real test, and you'll see, boom, 10 seconds. Okay, so it goes from 1 to 10, just almost instantaneously. So an extra 10 seconds got popped on for no reason. No, I'm not saying shenanigans. Maybe he just didn't realize the clock was screwed up. But obviously the clock was screwed up. And you can just tell by the rotation that they're moving at the same rate. And that timing is just wrong. It's 10 seconds off. So again, you can see same position, basically 22.5. This would be 22, or 12 and 12.5. So very close to the same speed. And you would, as guessed, you would imagine that the lighter total experiment, the lighter one is on the left, and this is the heavier one with the heavier blocks. This one weighs more on the bearing than the other one, so you would expect the one that weighs less to be causing less trouble with the bearing. So it should go a little faster. If it was an idealization, okay, you'd expect them to move exactly the same, because they have exactly the same weight on a lever, on a balance. So, alright, so we'll go to his video, and then I'll draw, and then I'll make the rest of the video for my regular audience. I'm hoping I can get this guy to watch this video. We'll see what happens. And recognize that he made a mistake. I'm hoping. Alright, so I'll be back. Alright, so here's the video I made 4 days ago, and I'll just play a little bit of it.
This video is all about the concept called rotational inertia. We're going to talk about what the definition is, how it can be found using experimental data, how it can be calculated given the mass and the shape of an object, and we're even...
So then he just talks about a bunch of other stuff in general, not fake, but less useful terms. Alright, so here's where he's discussing the experiments, and so the ones that are relevant is these two at the bottom, okay, where we have, let me just check to make sure you can see that, see it well enough, yeah, allergy or something, anyway. So you have a half mass essentially versus a full mass, a 0.5 versus a 0.25. So two light objects, twice the distance. That means twice the velocity that the full masses would be moving. All right, and he has the numbers for those things as saying what kind of torque they applied. Now I just showed you that the torque applied was exactly the same, in the sense that they both moved at exactly the same speed, indicating they had the same resistance to motion. They didn't have different inertias. And clearly he has the inertia numbers at 243 for the light one, which is much higher resistance to motion. That means it should have moved a lot slower. And 148 for the heavy masses, indicating they moved much faster, much freer, because they had much less inertia, resistance to motion. So obviously his numbers here, I would say, are wrong. Okay, these aren't accurate descriptions of the actual inertia, it goes to when they change the masses, you'd expect exactly a 2 to 1 difference. So what numbers have been messed up here? I'm not going to bother going through it all and try to figure out how he got these numbers from those experiments, when I just showed that clearly when you use the same mass to rotate the mechanism, these two came up with the same number. So these, whether it's 243 or whether it's 148, both of them should be the same number. Now I'd say they should be this 243 number because it's closer to when you double the mass, you obviously double the force required to move it. So, but I'm not gonna argue all that crud. So anyway, he goes through all the points about he does point out the friction, so he does indicate that there is some friction. I guess that's not the friction part. Friction is there. So the weight of the pipes, he uses that. No, so he doesn't put in any friction component, but he does put in the weight of the pipes, which obviously changes the internal, how much you're going to measure. If you're going to do the experiment, you have to put that stuff in to get the right numbers. But again, the 2-to-1 relationship in terms of a comparison between two numbers, whatever number I got for this one and whatever number I get for this one, the lever doesn't matter because it's moving exactly the same. The stick doesn't matter, whatever you want to call that. And again, if you go through what he calculates, he's just calculating using this r squared term, which just is the same thing as saying velocity squared. The r is connected to the velocity. Twice the distance, twice the velocity. Half the distance, 3 times the distance, 3 times the velocity. 4 times the distance, 4 times the velocity. So you can see they're just basically squaring, they're just creating another mv squared equation. And it's wrong. Yeah, okay. So anyway, in my opinion, this is this is how it is with all of these experiments where you challenge the kinetic energy theory, and the only way they can make it work is they have to make a mistake somewhere or do something even more malicious to screw it up. But the fact is, momentum does work and kinetic energy dismally fails in all of these mechanical systems, because you just can't change the fact that all you're doing, the only quantity that you're measuring that's real, is mass moving velocity. That's the only form of energy there is in the universe, and you can't make masses move for free, and you can never make the motion disappear. You can only exchange it. One object hits another object and they share their condition. And that's what's going to happen. They're going to exchange energies. But you can't make it go away. It always is going somewhere else. Every bit of motion in the universe has been somewhere previously. All of this was somewhere else. All the stuff that made this happen, motion, was somewhere else 1,000,000 years ago, doing something else. And it's been doing something somewhere forever, theoretically. Alright, so that's probably enough for that, and then we'll get to the comment and something else, right? I think that's all I have to say to this guy. So, Mr. whatever the name is again, right? Debbink. It's got to be called Debbink, right? It's no other way to pronounce that. It's unfortunate it's not like debunk. Then you could have a really, you'd really be mission-oriented. But anyway, so I think that's enough. I mean, the thing I wanted to add, just plainly asked, do you believe in the law of the lever? And do you recognize that it's the same energy to move a half mass at 2 velocity that it is to move a 1 mass at 1 velocity? I think I said that right. Half mass at 2, 1 mass at 1. Yeah. Okay. Anyway, so I'll take a pause and I'll go find the stupid comment and then point out how that is exactly what they're doing, in spite of what you're saying. I'm not wrong. Alright, so stupid commenter says, literally this is the formula, mv equals 1/2 mv squared. So that's how they come up with their more convoluted experiment, saying how much reflection you're going to get and how much goes into the mass. So when they do the 1-to-3 thing or the 1-to-2 thing, the formula they're using is based on that simple circumstance. So I'll play Professor Lewin saying it. Okay, anyway, so once again you have left me speechless. There are no words to describe how wrong that is. How did you come up with that? I came up with it by watching a Professor Lewin do it, and others, frankly. All right, so I'll go find the clip. All right, so here's the Professor Lewin clip. Now, the top formula obviously is MV, right? MV before equals MV1 plus MV2. So your outcome is, the two objects. One of them may be reflecting, one of them go forward, doesn't matter. So that's the momentum part. So this is this would be MV equals M1 V1, okay, because that's only one object moving. And now you have MV, the first object, plus the second object. So that's the momentum formula. And now he's just going to write the kinetic energy version of it.
M1 V1 squared, that was the kinetic energy before the collision, must be the kinetic energy after the collision. 1/2 M1 V1 prime squared plus 1/2 M2 V2 prime squared. This is my equation number 1, and this is my equation number 2. And
so that's what they're using, and now they're going to make those two things equivalent and then do a whole bunch of switching and crossing around. Now, he just points it out right here, and they can be solved. You can solve them, right? So he's not going to do it, but he's pointing out that this is what you do when you combine these two statements and you make them equal to 0 and then make them equal to each other. This is what you get.
They can be solved. You can solve them. They're solved in your book. I will simply give you the results because the results are very interesting to play with. That's what we will be doing today. V1 prime will be M1 minus M2 divided by M1 plus M2 times V1. And V2 prime will be 2M1.
So he's just saying the first object is this formula, the second object will be this formula. Okay, and that's extracted, simply put, out of basically making an equivalence between MV and 1/2 MV squared. That's all he really did.
Divided by M1 plus M2 times V1.
There. So,
the first thing
that's why I believe it, okay? Yeah, so if you're going to make your argument, then explain how Professor Lewin doesn't know what he's talking about and he doesn't know what he's doing. Now, I saw the woman who did the measuring the weight of an electron experiment. She did the same thing and even more overtly. I mean, I think she actually just writes MV equals 1/2 MV squared. So, this is just a more complicated form of exactly that same statement. This is all they were comparing, MV versus 1/2 MV squared. This is the equal sign. These two formulas are now going to be made equivalent. And this is the product of making them equivalent. All right, enough of that. All right, so back to the comment that I haven't really read. I never hit the more button. Oh, look, there's a whole bunch of it. Oh, good. It'll be stupid. All right, so the rotating lever experiment were done by Debbink Physics, not Despar. Same difference, right? I mean, he's playing the video and using the pieces to make some sort of argument, which, as I just showed, is a garbage argument. All right, Despar has just made a video for the comparison. Go watch the original video. So, yes, I did and found the obvious error. Okay. Anyway, your static friction argument makes no sense. So as I explained, one experiment does physically way more than the other experiment. So you can't argue they have the same friction on a bearing when one weighs almost twice as much. It weighs, minus the weight of the lever itself, clearly it weighs almost twice as much. The levers were spun with constant force, no rubber bands but weights, which again is a tricky definition of a constant force. And obviously when you move something in gravity, it can't weigh as much. So if something is actually moving, you can understand that it can't weigh as much. It can only weigh when there's a differential to something not moving. So obviously relative motion gets a little more complicated, and the force applied when there's relative motion. So I'd argue that rubber bands are frankly better than dropping weights. Where would the energy be stored for the bigger jolt? So again, it's obviously stored in the fact that the weight isn't moving. So if the object doesn't move because of static friction, obviously it's going to weigh more because it's not moving. If it's moving in the gravity, it can't be collecting the same amount of gravity per inch of motion, correct? So obviously that's the question to ask. Okay, and would that be free energy? And I don't know, how would it be free energy? So he's basically arguing there's no such thing as static friction. And everybody knows there's static friction. Everybody knows that you have to apply extra energy to get something started. And once it's started, you can apply half as much energy. Free energy gained by adding friction. So again, the friction has to be broken so it takes away energy. It doesn't add energy. And it was clearly displayed in the first experiment where it ground to a halt. And the only thing that could grind it to a halt was friction. There was no other place the energy could disappear to. It had to have disappeared to friction. Are you saying that objects fall down the faster, the longer they are held up before dropping them? I am saying that if you want to get a maximum amount of gravitational potential difference, yes, not moving is going to be heavier than moving. If you're pulling on a string while it's moving, obviously. Just as it's heavier if I drop it on a scale, it weighs more than if I put it on the scale. All right, so your problem, screw you, is that you judge all experimental evidence by your own axioms. Yes, that's right, of course I do. I judge them based on what I understand consistently to be true, and I'm quite confident levers do conserve momentum and they work. And the whole reason why they do work is because they do exactly what pulleys do, even more efficiently. And that is conserve momentum. They change a big mass and a little v into a little mass and a big V. That's what they do. Okay, and not the other way around. When a dead simple experiment. So again, I showed the big giant error in it in two respects. The giant friction problem, and in the second respect, the silly stopwatch jumping 10 seconds. So all this talk about how, oh, you're too suspicious and oh, blah, blah, and blah, 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 when obviously it is a garbage experiment. Now, whether this guy will admit it's a garbage experiment, who knows? But I just pointed out it's pretty garbage, right? It's pretty garbage to say it took 22 seconds when it obviously only took 12. All right. When a dead simple experiment like a pendulum collision completely disagrees with your axioms 100% of the time. So that isn't at all true. That's just lying. You really don't have any such evidence, and certainly you don't have it compiled by any scientist anywhere. So all you have is Dispar, the guy who just posted this crap as being legitimate, as your source. And, fuck you for that. And let's understand, physicist Michael, a frickin' college professor, was supposed to be doing the experiment, right? Brought all the materials and decided not to do it after all. So a big fail there. You should at least question their validity. The validity of what? You should at least question their validity. I don't know what. So he's saying my axioms are in trouble. They're not in trouble at all. You're not coming anywhere close to proving levers can't move a half mass twice the speed. It can only make it go 1.4. You're nowhere close to proving that a human being can't throw a half weight bowling ball twice as fast. You haven't proven any of that, only 0.4 faster. You haven't proven it taking 5 times the energy 25 times the fuel to spin something 5 times as fast. You're nowhere anywhere close to that. All right, and I've got the ballistic pendulums on my side. I have all the lever experiments on my side. I have and the crashing blocks on my side. So screw you that I'm the one that needs to question the validity of my axioms. You're obviously the one that needs to question them. The fact that you do not demand any evidence. You have nothing close to any evidence that 5 times thing. Right? You don't have any evidence that a turbine spinning 5 times as fast makes 25 times the electricity. You have nothing, no evidence supporting that nonsense. And yet you'll argue for it? All right. But what you do is that you come up with the most outrageous nonsense. Okay, so let's just understand. I come up with the outrageous nonsense of noticing the stopwatch jumped 10 seconds erroneously. And the nonsense that clearly the only thing that could have stopped the other thing from moving was friction. There's no other mechanism could have stopped it. And the wildest excuses, okay, for why the experiment didn't work. So, I mean, plainly, you've been, hoisted on your own word petards here, because clearly you're the one who didn't apply any scrutiny. You're the one who didn't look at the video and say, oh, wait a minute, that doesn't make any sense. Why did that stop? It shouldn't, once it started going, it should be easier to keep going. Why did it stop dead? So you're the one who's a flat earther. You're doing science like a flat earther. So fuck this. I don't have to take this crap. And I won't. I'll just block you again. You can make physics arguments, but if you can't make them without this idea that somehow I'm doing something wrong by applying reasonable arguments, and they're all reasonable arguments. You haven't debunked anything I have argued. All right, you're just pretending you can ignore every single bit of evidence I've shown and every bit of reasoning I've applied, and you can just debunk it by saying so. And that's just bullshit. The spaceship argument, again, are you disagreeing that if I calculate the kinetic energy of the thrust, it will do me no good, because the only thing that's going to move the spaceship is an opposite reaction to the momentum. The momentum of the thrust is what the rocket ship will equally react to. Are you going to deny that fucking basic truth and then still say the kinetic energy can do work when it can't do the simplest thing? Something is in space and you want to move it, and you throw something off of it, and your kinetic energy can't create an equal and opposite reaction. It can't make the spaceship move. And the only thing that can make it move is momentum. And you're going to make this argument that I'm the flat earther? Fuck you. All right. Enough of that. All right, so just in case there's somebody lingering about who doesn't know what this is all about, again, with the Steve Mould lever argument and what's being argued now to preserve kinetic energy. Again, they're going to destroy 1,000-year-old well-demonstrated reality. So if you have a lever, the law of the lever basically says, look, if this distance, right, any motion here is going to be twice the motion here. Okay, it's just a physical has to be. It can't happen any other way. If this moves 1 inch, this has to move 2 inches, okay? Because it's a physically rigid mechanism. It can't do it any other way. So if they move, they have to move in the same amount of time. So obviously this always has to be twice the velocity that you're going to have here, even without a mass. You know that this hunk of mass of the lever is going to move 1v, and this piece of the lever is going to move 2v, no matter what's on the lever. And so obviously the sensible thing you can do, okay, in spite of their vector nonsense that somehow direction matters, you can put energy in this direction and you can get almost all of it back here, okay, 95%, let's say. Losses to the lever itself you have to accept. But that has been well tested, let's just argue, by mankind in using levers. And the obvious thing they're using levers for is to create, where you're doing a very long motion over a long distance and you're creating a very high amount of torque at a very small distance. And that's what levers are used for, is to change the MV. All right. Even using your own body weight. I mean, that's how I've used most of the time using a lever. I mean, a couple of years ago I had to actually fix a sidewalk. Giant hunk of sidewalk, had to re-level it. And you're almost arguing that's not going to work. But I actually was able to get enough leverage to lift the whole giant piece of concrete up and re-level it. So I just used my gravitational weight, in a substantial way to do much of the work. Anyway, the MV gravity gives me. All right, gives us anyone. So obviously their argument here is this is what Steve Mould said. So for thousands of years, the understanding would be is that you could put a 2 mass, okay, going 1 velocity here, and you could have a 1 mass, and it would go 2 velocity here. Okay, and that would be the obvious exchange of your momentum. You took a big M and a small v, and you converted it into a small m and a big V, but the two will always have to equal. All right, and so as long as you get your distances correct, the proportionality is correct, you can have this be the same exact experiment as this. So the same motion of the lever, the same deceleration of the object, everything will be exactly the same because that's the law of the lever. Okay, this has to go twice as fast. If it's half the mass, it's going to feel like the same weight. And that's been the argument. If I put my finger on here, okay, and push on the lever, this is going to weigh the same as this. It's not going to weigh anything different. It's not going to apply any kind of different force. If they tie a force meter, okay, to the lever and push, they're going to find the same exact force creates these two outcomes. But they never done these. They won't do the experiments, right? So, I mean, obviously, Steve Mould says it only goes 0.4 faster. So instead of going twice as fast, it goes 1.4. Okay, only 0.4, an incredible degrade. Now, there are a couple of experiments that have been done, Brozo and myself. The Brozo experiment is more qualitative in the sense that he did calculate, did do the actual numbers. I just did it by impression, and clearly it looked like twice the velocity for sure. But in the Brozo case, okay, the 2 mass to navigate the a set amount of distance, it was that's the one slower, so that was the one that was 19 frames, and it was only 11 frames, okay, for the lighter object. So not 2 to 1, but damn close. Almost twice the speed. Not anything indicating 1.4. All right. So, but that's all we have as experiments. So, fact is, Steve Mould didn't do any experiments. He just made a claim that this is the way it is because we say so, and that's it. Kinetic energy theory says so, so therefore, screw the law of the lever, screw Newton, and it doesn't make any sense. I mean, what would be the source of this extra hardness in motion, in moving something? There's half the little bits to move. Why should it be in some way harder to move them twice the speed if there's half as many? It doesn't make any sense to argue there. That's some kind of problem. It's like saying a half of a sail on a boat. If you have half the sail that somehow you can't use, it's going to be more inertia. No, it's not going to be more. It's just such a bad theory. And to get all of this blowback and bullshit, instead of people just acknowledging that, yes, this physics is really messy, this MV squared thing, its history is garbage, okay, just the mere claim. Again, violating the law of the lever. Leibniz basically said 4 pounds dropped 1 foot is the same as 1 pound dropped 4 feet when they don't have the same momentum. We know they don't have the same momentum. One is twice as much momentum. And yet he says they do the same amount of work. But zero experiment proving it. Zero. Well, again, I could go ballistic pendulums, water wheels, all kinds of examples where kinetic energy dismally fails, and they just keep using these niche, rigged experiments to keep it afloat. And it's really disgraceful physics. It's disgraceful science. It's so bad. Again, they haven't improved any from Deschardelet's denting clay with round objects. It's all just theater, and there's no science here. All right, so enough said. Till the next time and such. There was something else I wanted to bring up, but I'm sure I'll have to make another video, so I guess you can wait till then. Shit. Hate this planet.